Well, today I want to talk about problem 11 in the sample midterm. I'm going to post it in time for you to use this to help with the WeBWorK set on series solutions. Okay, we've got a series solution centered at 0, which we almost always do. It's to a second order linear ODE. And this is the recurrence relation. So Cn plus 2 is some junk involving n times Cn for n equals 0, 1, 2, 3, etc. You're asked to find the first 3 non-zero terms unless the series terminates sooner in each of 2 linearly independent solutions, y1 and y2. And we're going to choose our favorite y1 and y2, where y1 has value 1 at x equals 0 and slope 0 at x equals 0. And y2 has value 0 and derivative or slope 1 at x equals 0. And then we're asked to indicate any exact solutions we find in this way. All right, there's sort of 2 ways to do this. I'm going to call it method A and method B. Method A, I'll do here. So here in method A, what you do is you just write down the recurrence relations, keep C0 and C1 arbitrary, solve for C2, C3, C4, solve for a few of the C's in terms of C0 and C1, which can always happen. And then you write down the solution and gather the terms that have a C0 in them and the terms that have a C1 in them. So you keep C0 and C1 arbitrary. Then solve for C2, C3, etc. And you get y is C0 times, you're going to get 1 plus something times x squared. You don't get an x term plus something times x to the 4th, and with this kind of symmetry, plus dot, 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 plus C1, something that starts with an x, and then it has something, and maybe it would have an x squared in general, but with this symmetry, it only has an x cubed plus something times x fifth. So this thing here is y1, and this part here is y2. And as I mentioned before, it's a little bit sad that the numbers differ, so don't let that confuse you. C0 is in front of y1, and C1 is in front of y2. Oh well. So method B, this is in the scanned solutions. So you get the recurrence relation like before, but you solve the recurrence relation twice. You set C0 equal 1, C0 equals 0. This gives y1. And if you set C0 is 0 and C1, that should be a 1. That gives y2, okay? So, let's just jump in and do it. I'm going to erase this in a minute, but I can write down all of the recurrence relations without doing that. Just a second, I'm going to get my black pen. I'm back. So what is the recurrence relation? Let's unpack it. The first time is when n equals 0. The first one of these infinitely many equations, and that is going to be C2, is when n is 0, I get a negative 3 over 2 times 1, C0. And when n is 1, I get C3, 1 plus 2 is 3, is 1 minus 3 is negative 2 over 3 times 2 times C1. When n is 2, I get C4 is minus 1. 2 minus 3 is negative 1 over 4 times 3 C2. When n is 3, I get C5 is, 0 over 5 times 4 C3. Well, that's important. Let's just pause there. That's a really important one. C5 is 0. And I can see it from here, right from the very beginning. It's good to look for a factor. Good to look for a time when the coefficient in front of Cn is 0 for some positive, some n in this regime here. Okay, let's just keep going. N is 4. I get C6 is, when n is 4, I get 4 minus 3, I get 1 over 6 times 5 times C4. And when n is 5, I get C7 is 2 over 7 times 6 times C5. All right. So I got these recurrence relations, okay? So while I'm erasing this, let's see. See, the idea of the recurrence relation is they didn't give me a formula for C sub 3852, right? I've got to figure out what the C's are. So I don't get a formula for Cn, I just kind of get a rule to how to find Cn. Okay. And then the very, very, very important thing about this is the recurrence relation never tells me what C0 and C1 are. C0 and C1 are arbitrary because the initial conditions to the ODE are arbitrary. Y of 0 is C0, and that's arbitrary. Y prime of 0 is C1, and that's arbitrary. All right, so let's see if we can solve these. This first one is C2 is minus 3 halves C0. That's okay. Let's put them over here. C2 is minus 3 halves C0. C3 is minus a third C1. I might want to keep the 3 times 2 if later I was going to try to find a formula for Cn. But I'm not doing that. I'm just trying to find the first 3 non-zero terms. So let's write C3 in its simplest form. C3 is minus a third C1. And then we have C4 is minus 1 over, let's write it as 4 times 3. But the important thing here, this is where it starts to kick in to be the normal thing. Writing over, I don't want to write over here C2 because C2 is already known. C2 is minus 3 halves C0, right? Right? C2 is minus 3 halves C0, right? It was minus 1 over 4 times 3 times C2. But I can always solve for any of the C's, the C sub large subscript in terms of C0 or C1. The 3's cancel, and I get plus an 8. Okay, and that's over here. C4 is 1/8 C0. Cool. And then C5 equals 0. We'll just simplify that. That's a complicated way to say 0. 0 over 5 times 4 times C3 is 0. Very important. C5 is 0. C6 is, who cares really? We don't care about C6. And we'll see that in a minute. You maybe want to solve for it. It wouldn't hurt. But I wanted to not just stop, because what is C7? Well, it's something times C5. Oh, but C5 is 0. So C7 is 0 as well. Right? C7 is 0. And what is C9? That's something times C7. So that's 0 as well. In fact, C9 equals C11 equals C2019 or C2020. That's 0 as well. 2021. C sub any odd, if that odd is 5 or bigger, is 0. Right? So let's just plug that in. Okay, let's write that down. C sub 2n plus 1 equals 0, as long as n is at least, what? When n is, I get 5, when n is 2, for n an integer greater than or equal to 2. Okay, if n is an integer greater than or equal to 2, then c sub 2n plus 1 is equal to 0. Right? If n is 1, I get, this becomes C3. That's not 0, but all right. So now I can erase all of this. I thought I could even erase the recurrence relation, but I think we have enough room without erasing it. All right, so now let's just write down the solution. Let's not forget the solution is y is c0 plus c1x plus c2x squared plus c3x cubed plus ... Let's not lose sight of that. That's what we're doing the whole time. That's what this says. And this might speak to you a little better. Okay, so let's now plug in what we got for C0 and C1. C0 is just C0. C1 is just C1. But C2 is now negative 3/2 C0. So it's negative 3/2 C0 x squared. C3 is negative 1/3 C1. So I have negative 1/3 C1 x cubed. Right? And then what plus C4? C4 is plus 1/8 C0 x to the 4th plus 0 times x fifth plus ... And let's not forget that I don't care what, there's some plus some C6 times x6 I don't care about, but there is plus 0 times C times x to the 7th, plus 0 times x to the 9th, etc. So now if you go back to this method A, is I keep C0 and C1 general, write the solution, and then I gather the terms that have a factor of C0. And what do I get when I factor out C0? I get a 1. Don't forget the 1 there. C0 times 1 minus 3/2 x squared. That's minus 3/2 times C0 times x squared. And then I also got a C0 times an 8 x to the 4th plus an 8 C0 times x4 plus, who cares? Right? Because they want 3 non-zero terms. I found 3 non-zero terms, and this is going to be, this is in fact the RY1, but let's just do that in a minute. Plus what's in front of C0? So what's in front of C1? There's this term. I think I'm going to use some colors here. We got the blue here. Those are the blue terms. And then we got the red terms. What multiplies C1? X, I took care of that term, minus 1/3 x cubed, plus 0 times x fifth, plus 0 times x7, plus 0 times x8. In other words, I'm just done. That's it. That is a solution. That's an exact solution right there. Right? So that's the underlined in red solution. All right. So now we can find, that's the question again. Find the first three non-zero terms unless the series terminates sooner. Okay, in each of two linearly independent series solutions, y1 and y2. And y1 is this guy because it satisfies that y1 of 0 is 1, y1 prime of 0 is 0. There's no x term. In other words, it's plus 0 times x. Here, y of 0 is 0, but y prime of 0 is 1. So that's the solutions. All right? The answer is y1 is 1 minus 3 halves x squared plus an eighth x fourth plus dot dot dot. And y2 is x minus a third x cubed. This is an exact solution. And they wanted me to indicate any exact solutions we find in this way. And as I mentioned before, that's one of the great powers of these series solutions is that they can find polynomial solutions that are exact. Okay, because the series for a polynomial terminates. All right. Well,